Alright, so let us go through this practice question now that you have given it a try. So for this question over here, uh, for part 1, right, in a previous video, I did mention that the length that they want you to find over here, xz, is actually this one that I highlighted here. Okay, so let's read the question a little first. They tell you that the diagram shows a triangle in a semicircle. So this is the triangle that they're referring to. Maybe let's keep the highlight on this triangle, and then this is the semicircle, right? So we can see that. And actually over here, straight away, you can you should be able to realize that this is already a property where if you have a triangle in a semicircle, right, where one end of it, or one end of the triangle, or um, because a triangle has three sides, right? So if you have one corner of the triangle being at the circumference of the circle, and then the other one being on the other circumference of the circle, and this triangle very nicely rests on, have one length being the diameter of the circle, then this is your classic right angle triangle in semicircle property um, for the circle properties from the circle properties chapter, right? So because of that, you should straight away be able to realize that this triangle is going to be a right angle triangle. Alright, so let me do some erasing. And then this triangle is the one I'm referring to. This is a right angle triangle. Where? This is the right angle. So you should be able to realize this, which is the thing that we will use to help us find the length of uh, xz. Okay. Apart from that, the question also tells you that this angle, right, uh, is 0.5 radian. So over here, um, your calculations for angle will be in radian, um, and we shall see a little more on how you process angles when they are given in radian. And they also tell you that the diameter is 32 cm. So this is 32 cm. Okay, so with that, let's find the length of xz. So if you realize that this is a right angle triangle, then things are a little more straightforward. To find the length of xz, we can use our trigo formula. So in this case, this is a right angle triangle, so I can use my Dorcaso. Um, if you are a little unsure or you need some recap on trigo before you are able to find the length of this xz, you can go ahead and check out the videos from the chapter of trigonometry. I have that in my course as well. So take a look and see whether you can understand. And perhaps after you do, right, you'll be able to find the length of xz. But back to this part. So this is actually your right angle triangle. So I'll use my Dorcaso, right? And then um, how we identify what to use, right, is by looking at what length as well as angle has been given to us. So this 0.5 will be the theta, all right? So if that's theta, I have theta, and I want to find xz. So according to this theta, this is your opposite because it's opposite to the angle. This is your adjacent, right? Because it's right beside the angle. So adjacent has this meaning of being right beside. So then this is your hypotenuse. The hypotenuse is always fixed. Reason because the hypotenuse will always be the longest side of the triangle, or the side that is opposite to your this right angle. All right, so with that, I actually have my hypotenuse and I want to find my opposite. So OH and theta, this will very nicely tell you that you need to use sine over here. Alright, because sine theta is over h, so that's why it's called so, right? So your tuaka so is actually TOACAHSOH. So just a very quick recap, right? So this is your so, or the one that is for your sine, where it's sine, then opposite and hypotenuse. Okay, now so with that, I can put in the angle here, right? So that is my 0.5 radian. And okay, let me erase this so that I have more space. And we want to find the length xz, and that's my opposite, so I'm just going to put it there. And then 32 is the hypotenuse. Now, how we get the answer is to treat sine 0.5 as a number. So if this is a number, you can put it as over 1. Right? So if sine 0.5 is like a number, you can just convert it into a fraction by making it over 1, right? Like 2 is actually 2 whole, so 2 over 1, right? That will still be 2. So just like that, I will have this as a fraction, and it's always easier to move things around for your tuakaso when you have both sides being a fraction. What do I mean, right? So if both sides are a fraction, I can just cross multiply. So when I cross multiply, sine 0.5 will multiply by 32, so that gives me 32 sine 0.5. And then 1 will multiply with xz to give me xz, right? So after that, by right, this 32 sine 0.5 will be here, and then xz will be on the right side. But because they are equal, so they are essentially the same thing, I can swap them around, so then they will still be equal, right? So that is what I did over here. Okay, so backtrack. With that, you will get this. So just put that into your calculator and you will get your xz. All right. So keep it in with more decimals first, right? With more significant figures first. Then after that, put it in terms of 3SF, because this is my final answer. So I'll be giving them the answer. So I will keep it as 3SF. Now, so that's part one, finding xv. Okay, so if you realize that you can use your tuakaso, you realize this is a right angle triangle, then it should be fairly straightforward. All right. Now, in part two, they want us to find the length of yz. So pretty much the same drill, right? So realize that the length is in a right angle triangle, use a torcaso to go and find your adjacent this time, right? Instead of your opposite. So going through that same thought process, right? I'll brainstorm and realize that, okay, I have theta. I want to find my adjacent, so A, and then I have my hypotenuse. After you find part one, you technically also have your opposite. So if you don't want to use your hypotenuse, right, you can say that I have O, I have A, I mean I'll find A, and then I have theta, so I can use tangent. All right, so that's just a very quick uh, revision. All right, for Tokaso. But over here, I chose to use hypotenuse because hypotenuse is given to us, right? In case you get part one wrong, then your opposite will be wrong, right? Then using that in your part two will be wrong too. So just a little technique to get a bit more marks in case you made a careless mistake in part one. Use back the hypotenuse because the hypotenuse is given to you in the question. So the length won't be wrong unless you, instead of 32, you put in some other value. All right, so that's a little tactic that I'm gonna uh, that I want to mention here. Now, okay, so that aside, the way to get your answer is pretty straightforward. I've already demonstrated just now. So make this over 1, cross multiply, right? So this will be 32 cosine 0.5. And then the other side will be 1 multiplied by yz. So this is it. And then I'll swap them around. And then I'll end up with this. All right. So put this, okay, let me erase this first. All right. So put this into your calculator. and then you will get this value with more decimal places, right? So this is our final answer in 3SF. Oh, one thing is that one thing to take note of is that your angle here is in radian. All right, so when you put into your calculator, cosine 0.5, sine 0.5, you need to make sure you're in the radian mode and not the degree mode. All right, because if you're in the degree mode, then the answer that you'll get will be very different. All right, so do take note when doing this Tokaso, when doing your sine, cosine, tangent, the mode that you're in matters. And that the mode that you will be in depends on whether your angle is given in radian or is it given in degree. Okay, if that's all right with you, we have found part 1 and part 2. We can move on to the area of triangle XYZ. So to find the area of triangle XYZ, now that you have already found this XZ as well as this YZ, is pretty straightforward. We can just, because and also if you realize that this is a right angle triangle, I can just half times base times height. All right, or you can have this as the base and then this as the height. But the idea of half times base times height is basically your base, which is a length, and your height, which is another length, in the triangle must be perpendicular to each other. They must be right angle away from each other before you can do this half times base times height thing, right? So kind of in a way, half times base times height will kind of only work for triangles where uh, okay, it will work for like right angle triangles, alright, or at least your base and your height must be right angle must be perpendicular to each other, right? So that's one thought. With that, you actually have learned another formula to find the area of triangle in your trigo chapter as well. So that is your half AB sine C, right? So these are the two methods that you have learned to find area of triangle. But over here for part 3, I'm just going to do half times base times height, right? Reason being is firstly, it's convenient. Secondly, later on, we'll do half AB sine C. So, I mean in part 4, right? So, yeah, we can just do half times base times height first, and then later on you can revise your half AB sine C. Okay, so part 3, very straightforward. Half times base times height. I wouldn't spend too much time explaining anymore. So just use the length that you found, and then multiply by half. Okay, and then 3SF because that's the final answer that I want. Okay, part 4, last part. Let me clear some space, so clear this out, and then we can talk about part 4, right? So give me a minute. Okay, so moving this back here. All right, part 4. So part 4 wants you to find the shaded area of the figure. Let's remove some drawings over here. Okay, I keep this triangle. So that is actually going to be referring to your this region here, all right, this shaded region. So to find this shaded region, I want to point out one thing first. This is a little this is an important point. Do not go and find the sector area of this. Alright, so some students at this stage, they would think that, okay, so I just find this sector area, this XYZ, and then multiply by this subtract, I mean, this right angle triangle, right? So getting a little messy. Let me redraw. So take this XYZ, right? They'll be like, oh, this is a sector, right? So I just find sector area of this XYZ. Then in red, you have this right angle triangle, right? And then subtract it away. The reason why doing this, you can't do this is because XYZ is not a sector. All right, so if it's not a sector, you cannot find a sector area. What do I mean by it's not a sector? So if you imagine this is a sector, then well, the pizza slice would look like, okay, it's gonna be humongous. So imagine this is the center of the circle for that circle, and then this is like the sector, right? Your circle won't be like this, right? Because completing this semicircle, this is the circle that I get. Instead, you'll get something way bigger, where this is the center of the circle, and then this is the radius, right? Perhaps then this makes sense to um, find the sector area of x, y, z. But if not, um, I want you to realize that this xyz is not a sector in this semicircle over here, right? In this semicircle, or even if you complete the circle. All right. So the concept of sector we previously mentioned in other videos also is this pizza slice idea, right? Where this must be the center of circle, this must be the radius, this is the slice. Now, and you'll realize that if I draw the circle, there'll be a part that's lacking. So it doesn't really fit into this red circle also, right? In case you're thinking, okay, so it fits into this red circle, all I have to do is just treat this as the radius, right? Then do my pi r square multiply by angle, right? Or angle over 2 pi. All right, so don't want you to think this way. Now, okay, so long story short, since I cannot find the sector of x, y, z, right? How am I going to find the shaded area, right, of the figure? So the sector that you want to find is this actually, this blue sector, x, o, z, right? X, o, z. And this one, if you think back to the concept of sector, makes perfect sense. Because imagine this is my whole circle. This is the piece of the pizza slice that I want to cut out, and I maybe want to find the area of, and then this is the angle, and then this is the radius, right? These are all radius. All right, so that actually is the area that we will be finding, right? This sector area XOZ. So how do we find the sector area of XOZ? So once you identify that this is the sector area that we want to find, the way to find it is actually going to be more straightforward already, because in previous question, in practice 1, we have already found we have already found sector area before, so it should be a little familiar. All right, now so let's go ahead and find the sector area. So that's what I did over here, but you realize that I need this blue angle, right? So to find this blue angle, first I'm gonna use a property to find the angle here. You can make use of a different property to find this angle. So a very common one is to first find this red color angle, right? Because you might realize that this is an isosceles triangle, right? This is the radius of your this circle, this red circle, and then this is also going to be the radius of the same red circle. Why? Because this is always the center of the circle, right? So wherever you have length that is stretching from the center of the circle to the circumference, that will actually be your radius, right? So this is radius, this is radius. So that actually gives you a very nice isosceles triangle over here for your OYZ, right? So if that's the case, you can take your okay, if it's in degree, then it's 180, right? But because it is now in radian, so maybe take your pi minus 0.5 minus 0.5 here, then you'll get this angle, right? And then take 100 and okay, take pi minus this angle that you get, and you get this blue one over here. All right, so that's one way to find a blue angle. Alternatively, what you can do is what I've done over here, which is to do exterior angle of a triangle, because this is a triangle. This OYZ, right? This is a triangle, and then this is getting a little messy, so let me just erase all this. So your OYZ is a triangle, and then you have this length that is extending out from that triangle. So this angle here is the exterior angle of this triangle, OYZ. All right. Um, if it's a bit hard to visualize, right? Um, Another way to think about it is, so this angle here is going to be 0.5 plus 0.5, right? Based on the property of exterior angle of a triangle. So it's going to be 1 radian. So let me write down 1 radian. So if it's hard to visualize that this blue angle is actually the exterior angle of the triangle OYZ, another way to convince you is actually to after you have done the previous method that I was saying, right, go and use the isosceles triangle, go and find this angle, you'll realize that you take 180 minus the red angle, or pi minus the red angle. So if you're going to take pi minus the red angle, right, to get this blue one over here, isn't that the same as if your triangle, which is going to be 180 also, in our case pi, subtract away these two angles? Just a very quick example, in case I lost you here, using degree, all right? Say this is like, may not be true, right? I haven't done the conversion, but imagine this is 30 degree. We already established that this is an isosceles triangle, so this side will be 30 degree as well. So very quickly, all right, using degree, you'll be able to realize that 180 minus this 30 minus this 30, right, is actually going to be 120. So your red one here is 120. All right. So using the first method that I told you, you will take 180 minus this 120, right? Say that because of angles on a straight line, and then you'll get this blue angle to be 60 degree. All right. So that's the first method. And what I'm trying to say is that if you cannot visualize the exterior angle of a triangle is actually this 30 plus 30 together to give you 60 degree, you can understand it on the numbers by seeing that if you take 180 minus 120, this red angle, you get 60 degree, right? And the same 180 degree minus your 120 here, you get these two angles. So that's why these two angles will be equal to this angle. So mathematically, they make sense um, based on angle properties. They make sense as well. All right. So yeah, going off tangent a little, right? Talking about this angle, but I hope that you can understand this exterior angle of a triangle over here. All right. So with that, since we already have the angle, we will be able to find this. Okay, let's remove everything. Find this XOZ, this sector. All right, and that is through our sector area formula, pi r square multiplied by the proportion of the angle, right? So that is your, since this is 1 radian, right? So that's why the angle is 1 radian over 2 pi radian, okay? So putting this into your calculator, you'll get 128 cm square. All right. If the answer that you put into calculator is a little like not that nice, right? Another way you can think of it is that uh, this pi and this pi will cancel out. So essentially, you're doing 16 square multiplied by half, right? Just so that you get you get this nice number over here, right? If not, to finish up, I want to get this shaded area, so I need to subtract away this triangle XOZ. So to get this area of this triangle XOZ, right, I will take the half AB sine C method that I mentioned, that is your second way of finding area of triangle, right? And I'll show you over here, right, how to do it. Now, why we are using half AB sine C over here is because this triangle right? This triangle is actually not a right angle triangle, so I cannot do half times base times height. So what I'm gonna do instead is I'm gonna realize that I have this length being 16, this length being 16. So if this is like my length labeled as A, this is my length labeled as B, right? So if XO is my length labeled as A, and OZ is my length labeled as B, right? Then this angle over here, this 1 radian, will be my angle C. All right, so very nicely multiply uh, half with 16, which is your A, 16, which is your B as well, right? And then the angle, sine 1. Punch it into the calculator, make sure you are in radian mode. You will be able to get the area of the triangle XOZ. Oops. Uh, yeah, so once you are able to find the area of the triangle XOZ, just take the sector area, this one here, subtract away this one here, right? And then that's what I did over here. You will find the area of the shaded figure. So I use the area of XOZ that has a bit more significant figures, a bit more decimals, so I get a bit more accurate answer here. But of course, because area of the shaded figure is my final answer, so I'll have 20.3 3SF. All right, so that is how you find the shaded area of the figure. Now, before I end off, I just want to talk about uh, how to find the length of the arc length xz really quickly. Why? Because earlier, right, in part 1, we mentioned that the length of xz that they want you to find here is actually the triangle length, right? This length over here. So in case you guys are wondering, how do I then find the arc length xz? Actually, if you can understand part 4, where I broke or where I showed you, right? I showed you this sector over here. You can use this sector to find your arc length. All right, so all you have to realize is that, okay, to find my arc length xz, this is the sector I'm looking at, right? And then this is the angle here, this 1 radian. And then do your pi, 2 pi r, right? Radius is this 16 cm. And then your proportion, so let me just write down here real quick, 2 times pi times your radius, which is 16, multiplied by your proportion, which is 1 radian over 2 pi. So very similar to what we do or what we did in part 4, where we are finding the sector area of this XOZ. Now I'm finding arc length of this same sector, right? So that's why the formula will be very similar. Put this into your calculator, you will get the arc length xz. Okay, so I just want to get this out there so that you also have a rough idea, a practice on how to find the arc length xz. So hopefully with this, you're able to understand how to use the arc length as well as the sector area formula a little better. And this concludes this chapter of arc length and sector area, and I'll see you in the next chapter.